Hello everyone, welcome back to the second part of lecture 6. So we ended the previous lecture where we wanted to calculate the entropy of an exponential distribution, so a random process that is characterized by the exponential distribution. And finally we wanted to verify the claim that the entropy measure and the variance of this exponentially distributed random process are closely related. So they are kind of sort of measuring the same thing, which is the variation, the variability of the random process, right? So let's begin by let's get to the calculation part of entropy. So we have x, which is distributed f of x, and f of x is given as lambda e to the power minus lambda x, such that x should be greater than or equal to 0, or we can write x belongs to the set begins close 0 and ends on open at infinity, right? Okay, so entropy measure by definition is 0 to infinity, a negative sign in the front, f of x ln f of x dx, right? This can be written as minus 0 to infinity. I'm going to put the value of f of x now, lambda e to the power minus lambda x log of the same thing, lambda e to the power minus lambda x whole thing times dx. We can write this further, we can simplify this further as minus 0 to infinity lambda e to the power minus lambda x ln lambda minus, or let's say plus ln of e to the power minus lambda x dx. So this finally turns out to be minus integration from 0 to infinity lambda e to the power minus lambda x, sorry about that, lambda x ln lambda minus e to the minus lambda x dx. Okay, so the entropy is given as the following: lambda ln lambda e to the power lambda x minus, so we can break these things into two entities, two different integration entities, minus let's say plus lambda integration x e to the power minus lambda x dx. In the first integrand, we can simply, because lambda and ln lambda are constants, so we can simply take them out. So I'm just gonna do that here. I'm going to first write minus lambda log lambda, and then write integration 0 to infinity e to the power minus lambda dx times plus lambda x e to the power minus lambda x dx. Okay, so we have the measure with us now. So we go on to the next page. We'll write this down again. So if we have E equals minus lambda ln lambda 0 to infinity e to the power minus lambda x dx plus lambda 0 to infinity x e to the power minus lambda x dx. Okay, so this is going to be lambda squared. I'm quickly going to go back and check that my calculations are correct. Okay, so I have minus lambda ln lambda 0 to infinity. Okay, this is correct. The first one is good. The second one is okay, I should have a square here. So plus lambda squared x into e to the power minus x dx, and this looks good as well. So what we are going to do is we are going to now integrate these two entities separately. So I'm going to now first solve out the first entity, which looks much simpler. This is going to be minus lambda ln lambda, which are just constants. When I integrate exponential to the power minus lambda x, I will simply end up with the following. And these have to be evaluated from bounds 0 to infinity, which are the bounds of x. So I can say minus lambda ln lambda e to the power minus lambda times infinity over lambda minus e to the power minus lambda 0 over lambda. Okay, so I'm multiplying lambda with 0 in the exponent. Now e to the power minus lambda times infinity is nothing but e to the power minus infinity here, so this will just reduce to 0. So this is just going to be 0. And the second component is e to the power 0, which is 1, right? So what I have is minus lambda ln lambda times minus 1 over lambda, which just simplifies to ln lambda. Okay. The second integrand is a little bit more complicated. So here I'm working with a situation where I must use integration by parts. So I'm going to call x as my first part and e to the power minus x as my second part. So integration by parts. Let's write down the formula. So we have, when we have f of x times g of x being integrated as a multiplier, that is given as this multiplication. Integration by parts is given as f of x is taken as first, integrand g of x is the second. This is given as f of x integral g of x dx. Okay, so this is multiplied here, minus integration del f by del x times integration gx dx whole integrated with respect to dx. Okay, so this is a integration by parts formula. We are going to apply it to this situation. So in applying integration by parts, I have f of x, which in my example is x, and g of x, which in my example is exponential to the power minus lambda x. So I'm simply going to follow the steps in the formula. So we have lambda squared, times f of x, which is just x, times integration of e to the power minus lambda x, which we have seen in the previous case. Here, right here, we can write this as e to the power minus lambda x by minus lambda, and this is bounded by 0 to infinity. So there is no upper bound, of course, but there is a lower bound which is 0. So we must evaluate this part like that. And we have that. Then we have the second component of integration by parts, which is this. So I have minus integration df by dx, which in this case will simply be 1, right? So del x by del x is 1, times integral of e to the power minus lambda x, which we have now learnt, x by minus lambda dx. Okay, so we are going to simply follow this through. We're going to solve for the first part, for which we are already aware of the bound, so we can evaluate it. So we have lambda squared. Lambda squared applies to both entities. So lambda squared times infinity e to the power minus lambda infinity over minus lambda minus 0 e to the power minus 0 lambda over minus lambda. Okay, so this is part 1, the first component of integration by parts. In the second component, I have a negative sign, and then I'm integrating e to the power minus lambda x over minus lambda. So minus lambda is simply as constant. So this will turn out to be e to the power minus lambda x over minus lambda into minus lambda. This whole thing evaluated with the bounds between 0 and infinity. Okay, so we have, and curly brackets closed, so we have lambda squared. So in this part, you have an exponent with a negative infinity sitting on it. So the first, portion of the first integral will be 0. minus is 0 obviously, so this is my first part will become 0 here, minus we have 1 over lambda squared times e to the power minus lambda infinity minus e to the power minus 0 lambda. So I have lambda squared times 0 minus 1 over lambda squared multiplied by minus 1. So I am left with just plus 1 as the solution to the second component. All right. So coming back to the fact that my entropy now is nothing but 1 plus log of 1 over lambda. We are going to toggle to previous screen and make sure that we have it correct on this page. So the entropy measure is equal to the first component plus the second component. So this first component plus the second component. The first component was solved to be ln lambda, right? And the second component is solved to be plus 1. So I have here 1 plus log 1 over lambda. Okay. So okay, so I've done a little bit of a fumble. So we are going to have negative or minus ln lambda on the previous slide. You can check my calculations again. Okay. Okay, so that's it. So we have arrived at a entropy measure for the exponential distribution. So remember, this is entropy for exponential distribution. And if you now go back and look at the different moments for the exponential distribution, so moments for exponential distribution that we had figured out in the previous, the first part of lecture 6, they were in the following order. So mu of x, where x is distributed exponential lambda, is 1 over lambda. Sigma squared x was 1 over lambda squared, and standard deviation was 1 over lambda. Hence, the entropy measure can be written as 1 plus log of the standard deviation. Standard deviation, which is just the square root of variance, is a measure for variation in the system, and the entropy measure turns out to be a monotonic transformation of the standard deviation. That means we are applying a log to the standard deviation measure. So if standard deviation is higher, then the log of standard deviation is higher, and 1 plus of this entity is also higher. So when SD increases, E increases, and SD increases if sigma square increases, right? So that means that higher variance is simply an information that is subsumed into the entropy measure as well. Therefore, what we are saying is that entropy and standard deviation are directly proportional to each other in case of an exponential distribution. Okay. Now, as a sort of a extension, because SD is simply square root of sigma squared, we can also say that entropy and sigma squared x are positively related or positively proportionally related. Okay. Therefore, we can say that entropy is an alternative measure of variability in a random process that sigma squared x provides us a value for. Okay. Now similarly, you can also you can say similarly for a normal distribution. So what is a normal distribution? Well, you can have a random variable x. It is distributed normally with mean mu and variance sigma squared. We can call them mu x and sigma squared x. Now here, x itself is a random variable. Mu x and sigma squared x, these are the parameters of the distribution. Distribution parameters. And f of x, which is the density function for a normal distribution, is given as, I'm sure many of you might be aware of this, is 1 over square root 2 pi sigma squared exponential of minus half xi minus mu the whole squared divided by sigma squared x. Okay, and you can show that exponential, the entropy measure for the normal distribution, entropy for normal distribution is given as half log of 2 pi plus 1 plus log of the standard deviation for the normal distribution. Standard deviation is nothing but sigma, right? Sigma x, which is the square root of the variance. Now, interestingly, even though the variance of a normal distribution and the shape of a normal distribution looks very different, the formulation of a normal distribution looks very different from the exponential distribution, very interestingly, the formulation where entropy and standard deviation are linked are very, very similar, right? Remember, for the case of exponential distribution, we showed a proof that entropy for exponential distribution was 1 plus log of the standard deviation. So in case of normal distribution, we have a very similar formulation, and hence we can infer that entropy and standard deviation are directly proportionally related, and also that the information that is contained in sigma squared x, which is a traditional variance measure, which provides us the variability of the states of nature that are comprised in a normally distributed random process, can very well be represented by an entropy measure as well. Okay, I am not providing you a proof of the the entropy measure for a normal distribution, but I encourage you strongly to go ahead and and complete this proof at your own time. This is a strongly encouraged assignment, but it will not be graded. So this is going to be left to you to complete. It will give you a lot of clarity to go through the proofs. So in case of mathematical statistics, I have said that we should always work with examples, and we should always look at how the data are behaving and the concepts are not sufficient. But on the other hand, it is also very, very important to conduct analytics, to go through proofs and go through the steps of proofs, because sometimes our understanding of the real world phenomenon enhances or increasing when we go through these proofs. We are able to understand what is this measure really trying to get us at, right? That process of getting to the final step, the final closed form solution, is very useful if you want to apply an understanding of entropy or adapt it to a certain real world situation. So I strongly encourage you to complete the proof with a rider that it will remain ungraded. So that's it. Okay, so now having established, we have established now that entropy is a we can provide an interpretation to entropy, which is quite similar to the interpretation that we have for the second moment of any distribution, which is the variance, right? The variability, the range with which a random variable can vary in a probabilistic environment. We should ask, why are we studying entropy to begin with? I mean, why do we, variance could have been sufficient, right? I mean, why do we need entropy? Well, the understanding of entropy provides us a very useful philosophy of technology, to begin with, right? It provides us an answer, why would we need technology, and why do we as human race, as government systems, invest so much in technological development through times. It provides us a statistical, mathematical understanding of the same, right? So that is comprised in what is called as the entropy inequality. This entropy inequality also is known as the law of entropy. Okay. Now, what is the law of entropy, and how does it sort of signify the importance of this measure, even though we had an alternative like sigma squared x, that's the variance, something that we are more used to as statisticians. Then why should we even care to learn things like entropy? So let's go back to our example where we had k states of nature given by I that goes from 1 to k, and we have probabilities attached to each state of nature, pi, which goes from p1, p2 to pk. Okay. Now let's arrange these probabilities in a vector. Okay, so we'll arrange or organize the probabilities in a vector P. So P is nothing but a k by 1 vector P1 to Pk that contains this information of all different probabilities that the states of nature can take. So P is quite comprehensive. It first of all identifies the indices I1 to k. I mean, that's an index on the probability. So we know that we are working with k states of nature, and we also know the probabilities attached to each state of nature. So P by itself is pretty comprehensive in describing the random process that we are working with. I mean, we can write P, we can take a transpose of P, and we will then get a row vector which goes from P1, P2 to Pk, right, which will be a 1 by k vector, 1 row and k columns. And now let's say this initial condition, say initial condition P prime, that is the original states of probabilities of the states of nature, the original state of the world, of the universe that we are working with, is transformed by an arbitrary deterministic transition matrix A, which has the dimension k by k. So what we are doing is we are transitioning the world that we are in to a new world of possibilities of these k states of nature. So what I'm going to say is that I'm going to transform P by a matrix A by simply such that I take P, which is a 1 by k matrix, and multiply it by this k by k deterministic matrix, and I get a new matrix, let's say Q. Q by itself will have the dimension 1 by k. So Q is nothing but a new vector of probabilities. So I have new vector of probabilities. So state 1, state of nature 1 will have a new probability after being transformed from the previous state. So I'm applying a transformation or a transition matrix onto P and getting a new state of the world or the state of universe called Q, right? So to see this process mathematically, if you are interested, I mean, you can look at, you can actually conduct some matrix operations and it becomes a little clearer. So I'm writing out P and then I can write out A. A will have, its constituents A11, A12, A1k, A21, A22, A2k, keep going, AK1, AK2, AKK. Okay, so this transition matrix is a k by k matrix. The matrix that I am transforming is a 1 by k matrix. So what am I going to get? I'm going to get a 1 by k matrix. How do I get this 1 by k matrix? I want the first element. I'll take the first row, that is the row vector, and multiply it by the first column. So I'm going to get summation I pi ai1. Second element summation I pi2, pi ai2. So what am I doing? I am simply taking a weighted average of all the probabilities and getting a new probability measure. I require this probability measure to be between 0 and 1. So each element of this row vector must be between 0 and 1. And secondly, when I sum all the elements of this new row vector Q, they must all sum to 1. So I am transitioning from universe 1 to a universe 2, which are delineated by the probabilistic nature of how these states will occur. For my example, for let's say prices of gold, if I am looking at a commodity price environment, and I have k different price levels that gold can take in universe 1, I have probabilities P attached to each state of or each price value or each price level that gold can take. I transition from this world to another world where the price levels remain the same. So gold still takes those k price levels, but with new probability measures given by the vector Q. Okay, so let's complete this, vector Q, right? So this is Q prime. So by the way, I should have had a 1 by k. So I'm writing a transpose of the column vector, right? So this is really just summation I pi ai1, I pi pi ai2, summation I pi ai3. Okay. All right. So what does the law of entropy suggest? So I have a state of world P, a state of world Q. We have started, the initial condition was P, the final condition is Q. So this is the final condition. So the law of entropy or the entropy inequality states that entropy inequality states that the entropy measure of state P prime A, we know how to calculate the entropy, which is a description of the variability of this random process, is at least as greater as the probability or the entropy or the variability of the initial condition of the probabilistic universe that we are studying, right? We can also write this as entropy of Q is greater than or equal to entropy of P, right? So a physical interpretation of the entropy inequality is that the universe tends to seek higher levels of entropy at each period or instance, at each period relative to the previous period. Okay, so as we move through time or through different universes, the universe that follows will tend to have higher variance, higher variability, higher possibilities, a greater degree of possibilities than the universe that we have just arrived from, right? So in such a world of ever enhancing, ever increasing entropies, technology is envisioned as a human intervention to slow down the process of how uncertain the future becomes to present, right? So let's write it down. So so I'm going to write down what is now, I'm going to call it the philosophy of technology, a philosophy. It's a philosophy of technology which comes from the idea of a universe being explained as a random process, right? It comes from the from the statistical understanding of the world. So I'm going to say, in such a world of ever increasing entropies, technology or technological development is envisioned as a human intervention that seeks to slow down, okay, that seeks to slow down the increase in entropy by constraining the evolving systems. Okay, so the idea is when I'm trying to put this constraint, so mathematically, if you want to understand what does it mean by constraining the evolving systems, what I'm trying to say is that is mathematically, if we want to go back to our, transition matrices and all that, when we transform, basically, this transition matrix, which was A k by k, to a matrix B k by k with this human intervention of technology. So B is the transition matrix with a human intervention. A was the transition matrix which would have appeared naturally. This transition would be such that the new state of the world, which is P times A versus P times B, what will happen is that P times B will be closer to P relative to what P times A was. Okay, so P times B is closer to P, so we are closer to the previous universe that we are transitioning from with human intervention versus when what we were if there were no human intervention. So that provides you a philosophy of technology, which can provide a rationale for why the human race or the governments all across the world are always trying to invest in better technology or a higher degree of technological advancements at any given point in time, right? So this is a philosophy. This explains the world with a perspective, right? I mean, the statistical perspective is not the only perspective out there, but it provides an explanation, a rationale for what type of happenings we see around us, in the world. Okay, so with that, I mean, there is one thing that although technology can slow down one pointer I want to give here is that technology can although slow down the increase, there are mathematical proofs that it can never reverse the process, right? So it can only slow down the process of ever expanding, entropies or the degree of variability that we experience in the world. Okay, so that's about it for this lecture, but I want to sort of end the lecture with this idea of what we are going to cover in the next lecture, which is spatial entropy. So now we have established that entropy is a measure of variability of a random process. What would spatial entropy be, right? You can try and think in your head, how would entropy be then understood as spatial entropy? Well, one of the things that will happen is that we will start to add this dimension of locationally delineated entropy. So entropy with a where component. So location wise differentiated variability of a random process would be spatial entropy. So where we'll begin next time is a model for a monocentric city. So here what we are going to try and do is use the concept of entropy to explain how cities are organized around us. So there is often a city center. The city center has quite a high level of activity going on. The population density is higher, prices are higher, and so on and so forth. And as we start to move away from this center, the population density becomes slower, the prices become lower, and so on and so forth, right? So the cost of living, the real estate prices, the population density, and so on and so forth. So spatial entropy will provide us a measure and an opportunity to model how cities are often organized around us. All right, so that's all for today's lecture. Thank you very much for your attention, and I look forward to having you over in the next lecture. Thank you.